Howdy, fundamentals of electrical engineering. So this is Topher. I'm here in Germany right now, so if you hear cars going by on the street, I apologize. I'm using my computer mic, might pick up some extra stuff. We'll talk about how microphones work actually in a little bit, so that'll be kind of cool. Anyway, so today I'm going to try to give you an overview of the fundamentals of electrical engineering, try to give you some basic principles, what we're trying to accomplish in this class. There's going to be a lot of review from physics, so if you remember your physics stuff real well, keep this as a nice little refresher, and if you don't, then go through it now so that we can knock it out of the way. A lot of the basic concepts we're going to start with are going to start building pretty quickly onto each other as we get through different types of circuits. So it's important not to just kind of know how the circuit works and the circuit diagram acts, but to actually truly fundamentally understand it. And it's that difference between a slight understanding and an absolute understanding that's going to be your ticket to success in this course. So with that ado, I'm going to try to go through a couple different things with you now, and I hope you have a lot of fun because I think this is going to be a cool class. So, on the screen right now you see a tear out for an iPhone. The iPhone's a really great example of a piece of electrical technology. They're ubiquitous, they're all over, we have them in almost everyone's pockets has some kind of smartphone. And the technology inside is pretty fascinating as well. You've got microphones, you've got a whole bunch of different systems in order to make that technology happen. So the question becomes to me, why is it important for a mechanical engineer or a textile engineer or an architectural engineer or any of the other engineers to understand electrical engineering? And I can give you a whole bunch of reasons for that, and we're going to work through some of those throughout the slideshow. But to begin with, in the iPhone, for example, let's just say you have two components, and components we describe as little tiny devices, little tiny pieces of electrical technology that exist on a circuit board. And these components, let's just say these two different components are put next to each other and they both heat up very hot. For the mechanical engineer, you have to make sure that the distance between these is acceptable so that you don't get coupling and overheating between those two devices, because that would ruin the phone. Another thing the mechanical engineer has to do is to be able to design the chassis, or this metal piece. Right here it looks like this aluminum was milled out on a milling machine. Milling is usually a pretty cheap process, especially for high batches. And it also gives very, very high tolerances as well, depending on how you do it and what type of computer control you have. So the mechanical engineer has to be able to fit all of these different electronics into the package or into the chassis. So it's important for them to understand what different components look like, size factors, form factors. So if a mechanical engineer doesn't understand an inductor and the specific form factor that it has, it's much harder to package that. And you might put that into a space where then all of a sudden you need more material around the side. More material costs a lot more money when you're doing hundreds of thousands, if not millions of different devices, different iPhones, or whatever the electronics you're trying to do are. So it's important to be able to understand the geometries, some of the specific electrical requirements of those parts. If you have a basic understanding of the circuit, when you look at the circuit diagram that the electrical engineer hands you, you'll be able to kind of follow it through. And that's important to be able to get connectors right, or to be able to do correct resistance, or to make sure that you have impedance matching if that's required. And there's about a lot of different parts of a circuit that the mechanical engineer needs to understand. So our goal in this course is going to be to try to get to a fundamental level of understanding of the circuits, to be able to understand if somebody gives you a circuit diagram in the future, what you have to do to be able to turn that from a drawing into an actual product. Another critical part of what we're trying to do here too is to give you enough mathematical background to pass the fundamentals of engineering exam, which is very important if you're going to try to go for your professional license someday. So without ado, we're going to get started and go into a little bit more detail of what it means to do electrical engineering. So, in Chapter 1, we're going to look at some of the circuit terminology early on. I'm going to try to show you some of the common terms that we have in electrical engineering, and the ones we also use in mechanical engineering sometimes. They're used interchangeably. And hopefully this is going to start out with a nice little background of what I'm talking about, so you can kind of follow along. So, Electronics generally are made of devices, circuits, and systems. So a device is a component. In the mechanical engineering world, we generally use the word component. In the electrical world, we generally use the word device. And that can be any single little piece. So like a resistor is a component, a capacitor is a component, an IC, which stands for integrated circuit, is a component. Uh, a transistor is a component or device. Depending on who you're talking to, each of these terms is acceptable. And individual components have two classifications with them. They're both active and passive. So a passive component essentially is, I think of it as a single in, a single out. It doesn't really have another set of electricity. So an active component has electricity which monitors or allows the control of electricity. So, for instance, if there's a signal coming into a piece, and that signal, as it gets louder or a stronger signal, allows more electricity to flow through it, that's a great example of an active. A passive is a piece where essentially the same amount of electricity flows in as flows out. There's nothing controlling that. So, a resistor is a great example of a passive device. You have a voltage in front of it, you have a current that goes through it. That resistor gets a little bit warm because it's dissipating some of the energy, but essentially you have no other control over the electrons except for the value of the resistor. Now, in retrospect to that, an active device, you might have a signal come in. So like an op amp is a great example of an active device, where as a signal increases as it comes in, it allows the increase of power outside of it. So generally active devices I also think of as a little bit more complex, because usually you have two inputs and one or more outputs. Two or more inputs and one or more outputs. As a passive device to me usually has one input and one output. So a circuit then, which we also in the mechanical engineering world call a CCA, or circuit card assembly. Circuits are a collection of different devices and components, a collection of different resistors and capacitors and other little components that you might have in order to do something. So an iPhone, for instance, has a circuit to control the microphone. There's a circuit in there to control the screen. There's a circuit in there to control the radio frequency signals and how the antenna works and how to receive and transmit signals. So each one of these is a separate circuit, and sometimes different circuits can be on the same PWB or circuit board, or sometimes there's different circuit boards in there that get connected with wires later on. But essentially the circuits are the part of the electronics that are doing something. And then the top level, we have systems and boxes. So in the satellite world, we call them boxes. The system essentially is the cell phone, the entire thing all wrapped up. How do all of these different circuits work together, and how do all of these different tiny components and devices work together to create something that essentially works as a single unit? So a satellite is a very complex system, and you have boxes inside of that control different parts of the satellite. It's very much similar to the cell phone and how that works. So essentially on this level we're going up in size too. So each device fits on a circuit, and the circuit fits within a system. Or each component, like a resistor, fits on a circuit board or a CCA, and that CCA fits into some kind of box or some kind of package thing where it all works together as a single piece. So as you increase too, the complexity goes up as well. So in this course, we're going to try to focus directly on understanding devices, understanding the components, what they do, what they work, how they work, what they look like, and then how to integrate them into circuits, which is the next level higher. And then towards the end of the course, we're going to try to do a project together where we have kind of a system that we're using multiple circuits to solve some kind of useful output. So there's two different methods of doing electrical engineering: analysis and synthesis, and we use both of these going back and forth. So analysis, generally you have a circuit that's already built or whatnot, and then you're trying to analyze the output of that circuit to determine its functionality. For synthesis, you have a set of specs that are given to you, and you're trying to design something around those specs to create a circuit to do that. So, for instance, when designing satellites, Generally, the customer, which let's just say U.S. government or NASA, NASA will give whoever's going to design the electronics some specs, saying, "Hey, we want this to be able to work in this temperature range. We want this to be able to work with this amount of power. We want to have functionality like microphone. We want to have functionality like cameras. We want to have functionality like gyroscope. We want to be able to take these type of readings." Those are all given in the specs to the electrical engineer. The electrical engineer synthesizes a circuit from those specs. So they look at the camera circuit, for instance, and they design a circuit for that camera. They look at the microphone, maybe, and they design a circuit for that. And each one of these kind of comes down to a very separate circuit that's designed. After these circuits are designed, they will take these and they will analyze them. And analysis can be with multimeters and plugging in individual pins into the circuit to measure the actual voltage and current at those specific spots. Or it could be a simulation on a computer where you have a circuit design on the computer and now you run a simulated current through it. And that gives you the output, which is your functionality. And then you look at that functionality, and maybe you have too much current going through a certain spot, or maybe you're not having the right amount of amplification for your camera, or different output criteria that might have to bring you back to the specs and back to a synthesis. So this circle kind of spins for a bit until you get a circuit or a box or a system that gives you the output that is acceptable and within parameters. So usually you're never going to get an absolute perfect circuit, but you can usually get things within a couple percentage points, or maybe even a thousandth of percentage point if that's required. And that's kind of the engineering trade-off that we have for systems, for electrical systems. So here we have a basic diagram of cell phone architecture. So we call this a block diagram. There's not really any circuits in there, but this allows us to set up the systems, if you remember from the previous slide. This allows us to set up the systems in kind of an organized manner so that we can start to tackle each individual system. So when you're starting with a very complex system, a very complex idea like a cell phone, you want to break those into smaller subsystems so that you can begin to tackle them and assign them to different engineers to work on. And that way you can all work in parallel to get things done quicker. So cell phone architecture is pretty cool. Cell phone architecture, you start with your inputs, so those would be like human interface, dialing, memory. You have to make a call on the phone before you can talk to someone. So whenever you type in on the screen your friend's number, or you look in the contacts to be able to find them, that's kind of the input, and that's being handled by a microprocessor control, which you can think of as the computer or the brains of the cell phone. And that microprocessor control can send information back and forth to the human user, or take information from the human user and put it back to do something with. So if you're going to try to make a call, you're going to type in your contact or hit your contact on the phone, and microprocessor control is going to send a small signal to the transmitter and say, "Transmitter, I'm ready to start sending something out. I'm ready to start sending a message through the antenna." And so at the same time, your microphone is going to kick on, and your speech, video, and data, which is another input-output on the other side, is going to start being converted by an analog to digital or a digital to analog converter. So an analog to digital converter takes a system or a signal like voice, which goes up and down, woo, woo, and that breaks it into a digital ones and zeros so that the computer can control it. And that is going to be sent to the transmitter, those ones and zeros, because we generally use digital transmission now. And that, once that's combined with essentially the phone number, you're going to send that through a diplexer, which a diplexer kind of controls how the antenna works. It controls if the antenna is receiving data or transmitting data, because a lot of phones right now are trying to save on space, save on money, save on extra parts, and they use the same antenna to both receive signals and transmit signals. So a diplexer plays a critical role in going into that. It's one of the major components of RF, or radio frequency engineering, which is pretty cool itself. So anyway, that's going to send your signal out. You've just said something to your friend. Now that's all going to bounce around in the cell towers and the cell phone tower architecture. They're going to talk to you. Your friend's going to send a signal back to you. That signal is going to come through the antenna again. It's going to be your receive signal. And your diplexer is going to send that to the receiver, which is built in. So you have the RX chip and the TX chip, the RX part of the circuit, the TX part of the circuit. That receiver is going to go back to a digital to analog converter. It's going to take all those ones and zeros and turn that back into a sound that your ear can hear, and that's going to be spit to your essentially your output, your headphones or whatever you're using to listen to it. So the point we're trying to get, the specifics on this aren't as important. It's a lot more complicated than this. But the important part to understand here is that we take big systems and we break them into subsystems. And these subsystems can talk to each other. And defining the parameters of how they talk to each other, whether it's a digital communication or an analog to digital converter that does essentially the translation of the signal, that's kind of what we're looking at in this course, is how do we break these large subsystems down to small subsystems that we can actually work with, and then modify them and then put them back into the larger subsystem. Hi guys, so we've seen all of these units many times in the past. I just want to stress that these are really important to know. You should have these memorized by now. If not, use this week to help memorize these so that you never have to look them up again, because it's a real pain to have to go to Google every single time you want to do a quick measurement or quick conversion. So most important ones on this are, of course, we're going to use time, seconds a lot in electrical engineering to be able to examine the influence of current over time or voltage over time or signals going through it. A lot of that has to do with time. For electrical current, the unit is amperes that we're going to use. Another unit in electrical that we're going to use a lot are volts, and we're going to go through what volts are in a little bit too. Temperature, kelvins, that's important if you're going to do anything with thermal analysis of circuits or whatnot. Mole is the amount of material. We don't use that as much in electrical, but down below we have a whole bunch of different prefixes in different magnitudes. So these prefixes are pretty important too. I'm just going to go through, just for fun, what I think of when I see the prefix and how that might relate to electrical. Exa, I actually don't really use that. I've never really used an electrical, so I don't really have anything I'm going to think about. It's a huge number though. So petaflops I think of, so supercomputing, how much power supercomputers have, how many operations they can do per second. That's an important thing. Tera, right now we have terabyte hard drives. That's another important one that's come out. Gigabyte, which is like flash drives, that kind of thing. It's a bit smaller than terabytes. Mega and kilo, the first thing that comes to my mind is mega ohm and kilo ohm resistors. And we're going to talk about resistors and what part they play in electrical engineering soon. For the milli, micro, those can come, two things come to mind. They come for like milling and that kind of processes. Excuse me, if we're trying to make a chassis to hold some electronics, how many mils of clearance, and a mil is 1,000th of an inch, so you can tell which one of these kind of fits on that. Another one, micro, nano, pico, I think of capacitors, so a microfarad or a nanofarad capacitor, a picofarad capacitor. Sometimes we even get as small as femtofarad capacitors. Those are all different units I associate with capacitors and capacitance. And then we have the atto at the bottom, which again is one like the exa I haven't really used, but it's a good one to know as well. So, in general, we use lowercase letters in electrical engineering to represent general cases. So, I, for instance, is the symbol we assign for current. I might or might not be time varying. We don't really know. We haven't really set that up ahead of time. So if you have 3 amps of current going through a wire, which is a fair bit of current, we would probably specify I equals 3 amps. So the next one, though, that we have is lowercase followed by a t. That emphasizes a time-valued quantity of time domain. So I parentheses t close parentheses could mean the amount of current going through a wire at a given time. So at time 0, maybe the circuit isn't plugged in, so I of t equals 0. And then maybe as soon as we plug the circuit in, we have 3 amps of current going through it. So 3 amps of current, that would make it shoot up real fast, and that's at time whatever we plug in. So any time after 0 is going to have 3 until we unplug it. So that's just another general case, and you'll see a lot of these going on. We use an upper letter case if the quantity is not time varying. So specifically, if we use uppercase I, if there's a constant value, so current always equals 3 amps. That's another way of doing it. And then a letter printed in boldface is used to denote special meaning. So I bold has a specific meaning, like a vector or a matrix or a phasor counterpart. And we'll get to that when we get to AC analysis. So when we're doing Laplacian or Fourier transforms, that might come into play as well for I of t. So Laplacian and Fourier are pretty cool. They're signal analysis. They're essentially, you can think of them as ways to get patterns out of a scrambling of data. We'll think of it like that now, and then we'll get to a much more specific definition when that comes up later in the semester. So here in circuits or electrical engineering, we're going to look at a couple different ways of doing circuit representation. On the left side, you see a very simple circuit representation. So this is just kind of almost a block drawing, a block diagram with some pictures to kind of show what's going on. Sometimes these drawings can be very helpful to explain electrical engineering concepts to non-electrical people. So, for instance, this quick one shows some kind of pad with a sensor and an LED, and then the bottom one is showing if I touch the pad, something happens to that sensor, and the voltage is going to go from 0 to 1.5 volt, and that's going to turn on the LED. So we've kind of used pictures to describe some kind of electrical concept here. However, these pictures are not very detailed. So right now, how is that sensor working? How is that being wired so that the power goes through? Where is the power source in this? Or is this a wall source? Is this a battery? Are we using some kind of capacitor to charge and hold charge to be able to light the LED up? There's just not enough information for this. So this gives a good kind of description of what's happening. It gives you, hey, I have some kind of input and that's doing this output, and the sensor is in between that managing it. But other than that, it doesn't give us enough information. We can't run a series of tests. We can't say what happens if the voltage is at 3 volts instead of 1.5, or what happens if we don't plug the sensor in? Will the light come on? Or what level of pressure do we need at the sensor to turn the light on? There's just not enough information. So in electrical engineering, we're going to start looking at how we can get that needed level of information. So if we look at the top, we're going to work down from an actual circuit down to the circuit diagram. Then we're going to talk about working back up. So in the top, in picture A, we have an actual circuit. So mechanical engineers like to call this a CCA, or a circuit card assembly. And it's an assembly because you have lots of different components or parts on that circuit card. So over, you see a metal plate. That metal plate could be for thermal reasons, to be able to pull some extra heat out of some kind of component that goes on top of it. You have a 5-volt power supply to be connected over there on the side. So that's kind of like you're going to have 2 pins come in, maybe some kind of connector, and we'll talk about connectors later on. We've got an IC, which stands for integrated controller, and that has essentially a computer chip inside of it. You can think of it as a little brain of whatever circuit you're working with. We've got some resistors, and that allows essentially the power that comes in from the 5-volt power supply not to burn out your IC, which is very important because you want your ICs to work for a long time. And then, of course, you have some kind of output voltage. So that is essentially what's coming out, or a signal that comes out, or is it pulsing? Is it just a lower, we don't know right now, but it gives a little bit more description on to what is happening than that other picture that we have before. So the next bit that we have is the PC board, and this is solidly in the realm of mechanical engineering. The PC board contains all of essentially the wires that connect the different components together. So those individual components, like the capacitor, the resistor, the ICs, all have to sit and connect in a proper way. Now, you could do that with a breadboard and kind of hook them up, or you can solder individual wires. They call that, what is the name for that? I think it's bugging. Like you have a little circuit bug, which all the individual pieces are wired together. It's very messy and it's not very reliable, and doing it, you have to do it by hand. So over time, we've had the ingenuity to be able to do these PC boards, which these have a whole bunch of different methods to make, and they're very cheap to make too currently. You can get small PCB boards manufactured for you for a couple dollars a piece and shipped to your house. This one right here we call this a single side PCB board. As long as I can see, there's not really anything else happening. It looks like maybe a double side PCB board. But essentially that holds all the components together and allows you to connect all the wires in the correct spots so that things don't essentially touch and short out, because a short could mean that your part burns out, blows up, stinks, releases the smoke of death. If you ever smell, by the way, ICs that burn, you'll know the smell very, very immediately. Electronics have a very specific smell when they burn out. But anyway, so that's the PC board in B, and then C is the circuit diagram of how the individual board works. So all of these work together to be able to determine what's going on. So each one gives a little bit more information as well. So if we look at the circuit diagram here, you see we have an op amp in there, we have an input, we have an output. So to me it looks like what we have here is some kind of sensor input that's going to come in around at the green spot, wherever we're going to push that sensor, some kind of capacitance sensor. It's going to be powered by some 5-volt power supply, and as you press it, there's going to be some kind of signal analysis that goes on, some filtering of the signal, and that's going to be bounced up by the op amp there to make a louder signal coming out. So it looks like probably this circuit's primary goal is, if you touch the pad, the more you touch it, or the higher capacitance that you have, the increased the output. Maybe that output goes to an LED, maybe that goes to some motors, we don't know because it doesn't say. But this essentially is kind of a subsystem, a circuit inside of a larger system. We don't know exactly what this output is going to be doing right now. The picture on the left shows an LED. On the right, it looks like we just have a connector, so maybe an LED plugs into that. Maybe there's another set of electronics for the LED. We're not sure now, but in general, we want to use as much detail as possible for circuit representation, so that's why we do the circuit diagram. And for a lot of things that we're going to work on in class, we're going to analyze these circuit diagrams, we're going to simulate them, we're going to test them, we're going to build them, and hopefully towards the end of the course, if we get time, we're going to be able to send some PC boards, or PCB board. PCB stands for PC board, or PWB is another word for it, which is printed wafer board, or printed circuit board for PCB. But hopefully we're going to be able to send some of these out to get machined, and then, or make them ourselves, and then maybe we're going to order some parts and design something at the top, which is an actual circuit. So you might recognize this slide actually from when I was trying to show and introduce what electronics packaging engineering is. But it's also a really good slide to kind of demonstrate the electronics manufacturing process. So in general, let's just say we're going to work with satellites for now, or cell phones. Any of the electrical systems, it doesn't really matter which you're going for. The process is the same. What happens generally is an electrical engineer, if they're trying to build a satellite, will get a set of specifications from NASA or whoever the person buying the satellite is, saying, we want our satellite to do this. We want it to take pictures, we want it to take temperature readings, and we want it to transmit them using an antenna back to Earth. So an electrical engineer is going to sit down and run some calculations, some initial hand calculations, to be able to determine, hey, these are some of the things we need. We need a power supply unit. We need a transmitter. We need a camera. This camera needs to be controlled with this kind of circuit. So they're going to run a lot of math initially and some simulation. And in order, after you run that, in order to create some kind of circuit, you're going to build what we call breadboarded circuits. So breadboarded circuits are quick and kind of dirty ways of being able to test out some of the math to make sure it works. And if the math doesn't work, you're going to have an iterative process. So it's going to go back and you're going to rerun the equations. Then you're going to try changing maybe a resistor value on that breadboard. Or maybe you're going to try to change a new op amp if your old op amp doesn't give you the quality that you're looking for. Or maybe you're going to change different LEDs because the manufacturer ran out. For whatever reason, between these first two pictures, the math and the analysis, it's going to iterate back and forth. So part of analysis too is not just the breadboard part, but also simulating these. So we're going to have some fun this semester doing some simulation on the computer with the box that came with your book. And that's going to allow us to simulate and test some of the circuits we design. Because ideally you don't want to design a circuit that doesn't do exactly what you want and then learn that later in the process when you've built 1,000 of them and then have to go back through. You lose a lot of money there. So after you design a circuit, after it works, and after you're absolutely sure that this is exactly what you want, the electrical engineer we'll create something called a schematic. And the schematic is the top in the top right-hand side in the blue box here. And the schematic essentially is a circuit diagram that shows how everything is connected and where different parts are, and has all of the electrical knowledge of that circuit. So where are the resistors? Where do we have wiring between? What is connected to what? Do we need connectors here? How is this connecting to the outside world? And so there's a whole bunch of very cool technical knowledge that comes in these diagrams. What does not come in these diagrams is the length of the wires doesn't matter, because in electrical engineering, electrical engineers don't look generally at the geometries of things. So none of these pieces are drawn to scale. They're all symbols. A resistor on here might be the same size as an inductor, might be the same size as an ID, but that's just on the drawing. That's not in real life. The electrical engineer is only concerned with how the different voltages and currents fit together, how the signals fit together, what kind of circuits are we using, what kind of ICs. So that's what's specified. So if you want to drag some of these wires out to make them longer or shorter, that's totally fine. It's the same circuit, even if you move parts around, as long as they're connected in the same way. Now, in the bottom, we have the green, and that's the domain of the mechanical engineer. And in the mechanical engineer, you're going to take that circuit diagram, that piece of paper, and you're going to turn it into something real, and that's your domain. As how do you get from a diagram to something real in the real world? And the first part of that after is you're going to design the PCB, or the circuit board itself. And there's a whole bunch of things you have to know about the electrical circuit and the schematic before you do that. You have to know which parts get hot, where they're located, so you don't have parts that burn out. You have to make sure that parts that need electromagnetic interference shielding aren't near each other, because you'll have interference between them. You need to make sure that you can design for manufacturability, that the circuit board is essentially a standard kind of size and follows standard hole dimensions. You need to know where to put thermal vias to remove some thermal heat. So without an understanding of that circuit or how that circuit works, you're not going to be able to do your job of taking that circuit and turning it into something real. So that's where your first step starts. The middle one, we call that a CCA, or circuit card assembly. After you've designed your circuit, you're going to populate it with the parts that the electrical engineer tells you to. So these parts come from the schematic. You don't get to pick them. However, you do have to make sure that all these parts fit. If you put two inductors real close to each other, they might not fit on the board and you're going to have problems. Or if you're trying to build something thin like an iPhone, you're going to have to make sure that all your parts have a very clean and small form factor. So you might change companies for some parts in order to make sure they fit on the board. And then finally, the last one on the bottom right is the manufacturer, the chassis design. So every single part inside of there is a physical part, and that's designed by a mechanical engineer. So the SIM card holder, that is a machined part that a mechanical engineer has designed. The chassis that holds all of these parts together, the screws, knowing where the screw holes go, knowing where you put heat sinks, knowing where the camera is going to be so that doesn't interfere with maybe the battery, which is a bit thicker on the back. All of those are part of the mechanical engineering domain. So as a mechanical engineer, you need to know early on how the schematic works, and even go back further to how the different equations work to fulfill the circuit's intentions or the system's intentions. If you know something has 135 volts and 1 amp of current, you know that's going to have a lot of wattage, and wattage is heat, and heat means you have to place that part separate and away from other parts so things don't overheat. So you're going to have to be able to run these numbers yourself, and that's kind of the domain of the mechanical engineer. As things get more and more complex, the electrical engineer takes over more and more of the circuit diagram, and the mechanical engineer takes more and more of the mechanical processes and manufacturing processes. However, they both have to know what the other person is doing in order to get a proper design. So I just briefly mentioned thermal coupling in a circuit, and I just briefly wanted to go through that. Thermal is heavily a mechanical engineering domain topic. We have multiple thermal classes that you have to get through for your degree. And so on the left, we have a picture of a circuit board with essentially a thermal heat map of it. And as you can see, there's a red section that's kind of, we call that thermocoupling. It's covering multiple components. And this is very, very undesirable because you can overheat other components very quickly that way. And sometimes thermocoupling can be so bad that you can ruin the shelf life of your iPhone, and cut it in half or maybe even a tenth. So instead of having an iPhone that works for 5 years, you have an iPhone that works for a week. That's not acceptable if you're trying to do any kind of electrical system. So on the right, we have a properly computed thermal model for a circuit board. As you can see, each one of the parts stays within its own thermal realm. There's some coupling in the green there, but we're presuming that essentially, for all intents and purposes, that this is a pretty well modeled and well approximated circuit. That red piece in the middle, you'd have to check the data sheet to make sure that's not getting too hot. And you have to remember, what makes heat? Heat is often done by resistance. Heat is a product of the voltage and the current that goes through that part. Heat is measured in watts. So again, we need to be able to understand the circuit to know where wattage is being consumed in that circuit so that we can design around it. And that's another part of electrical that overlaps into mechanical engineering. So on this slide, I just want to go through some common circuit elements. There's some different variations depending on essentially who's drawing it. There's variations between the American system and the European system, especially in resistors. I much prefer the American system. So what's shown here is generally the American systems. Again, there's even variations within that, but some of them always say the same for the American system, like resistors and capacitors and inductors. Those are very common. Those are the most common ones we're going to use. So I'm not going to go too much into depth in these. You should know these and have these memorized as to what the symbols mean because you're going to see them very, very often. Just to pull out a few that are important. When in the two conductors electrically joined at node A, anytime you have two things that cross over, we presume that there's a dot of solder in between them. So think of them as two wires with a giant glob of solder in the middle, and that makes them connected electrically at that point. If we don't want them connected electrically, then we use, to the right, the two conductors not joined electrically. And that little bump out shows that that wire is going over the other one. It's not actually touching it. If it's not touching it, then it's not connected. There's no imaginary blob of solder there. That's how I think of it. Other than that, fixed value resistor we're going to use a lot. Capacitors, variable resistors is like a potentiometer. Generally, it's a resistor that changes on something, whether the change is you turning something or maybe light coming into it or maybe heat. Some sensors are variable resistors. There's a whole bunch of different ones. We all kind of approximate how they look with the variable resistor symbol unless otherwise noted. Capacitors are another one we use a lot. Inductors. So batteries, DC versus AC. So there's an interesting one. So DC stands for direct current source. AC stands for alternating current source. So alternating current, generally we get a sine wave. We do some more math on that. Generally DC to me is a little easier to understand early on. You have a direct current, 10 volts going through. It doesn't change throughout its process. Up at the top, we have a current source. We have switches, so that's like a light switch if you connect it or disconnect it. The triangular one is operational amplifier. We're going to work with those a lot. Essentially, from a very basic perspective, an operational amplifier takes some kind of signal and amplifies it, makes it louder. But we can do a lot of different things with that. So like there's differential operational amplifiers, which can take two signals and amplify the difference between them, which is used a lot in biomedical applications. We have a whole bunch of different amplifiers and ways of using operational amplifiers. You could do some really complex math actually with operational amplifiers as well, which we're going to try to touch some of that later in the course. But they're pretty cool. They're a neat little IC. We have transistors, which we're going to get to again. Transistor, a very simple way of using them is if you have power coming into one terminal, you can have current flowing through the other, from one to the other. So essentially a transistor, in a most basic sense, can be used as an electronic switch or an electronic push button. Although there's much, much more complex things you can do with them if you're looking right around their point of saturation or right under their point of saturation as well. We have a voltmeter. A voltmeter, I'll show you how to use those in lab. Those measure, obviously, volts in a circuit. We have an ammeter, which measures the amps or current in a circuit. A dependent voltage source and a dependent current source. Both of those essentially are saying that something in the circuit changes the way that they output, changes the way that they put in voltage, or changes the way they put in current. And then finally we have a light-emitting diode. So a diode controls the flow of electricity in one direction. It controls the flow of current in one direction. And light-emitting diodes, or LEDs, as that electricity flows through the diode, if it's controlled properly, it emits light or photons, and those can be seen in your eye. So we're going to go through these in more detail later on as we get to the individual parts, but for now you should familiarize yourself with the individual symbols, because these are going to be very important. They're going to come up again and again, and there's no way you're going to be able to solve a circuit if you don't know the difference between what an inductor symbol looks like and what an operational amplifier symbol looks like. So here we have series and parallel connections. We're going to do a couple basic circuits with them. This should be review from physics. You've probably had this before, but I want to make sure we're all refreshed on the same point, because there's two very important concepts here that we're going to use in more complex ways in the course. So the complex concept that we're going to look at is in-series circuits have the same current. So if we look at picture A on the top right, we have a series circuit, which means we have a battery which is in series or in line with a light bulb, which is in line with another light bulb, which is back in line with the battery. So you have an output from a battery becomes the input to the first light bulb, and you have that becoming the input to the second light bulb, and the output from that coming back to the battery. So essentially it all flows in a loop. You have a single loop system here. So the important thing to note is the current any place in this diagram in picture A is the same. So if you look at the current before the first light bulb, or in between the two light bulbs, or after the second light bulb, the current is always going to be the same. If you have 1 amp of current coming out of the battery, you're going to have 1 amp of current coming back through the battery. Current is conserved in this system. Now, in parallel, the important concept is you're going to have the same voltage at those points. So if we look at picture B, the battery is going to output, let's just say 5 volts. 5 volts is going to go into both of those light bulbs. The only thing that's going to change is the current, though, because essentially here you have a split, and that split is going to be a current divider. And that split there, you can kind of see where you have one line coming in, you have an extraordinary node, which we talked about briefly before, and that's going to split the current into the two. So actually, another word for this circuit that we're going to get into later is the second circuit, picture B, is a current divider circuit, and the first circuit, picture A, is a voltage divider circuit. We're going to get into that more in the mathematics behind it, but right now, make sure that you have memorized in series circuits, the current is the same, and in parallel circuits, the voltage is the same. So here we're going to go through some circuit topology. Essentially, I like to think of this as the way the circuit connects together, or the way you put wires in a circuit, which isn't technically correct, but to me, thinking about it in terms of wires helps me visualize what's going on. So the first term we have in red here is branch, which is a single element. So it's a single component, like a resistor, or a source, or a capacitor, or an inductor. How we plug those into the circuit. So all of the things in blue here are branches. So you should be able also at this time to describe all of the blue symbols, which one's an inductor, which one's a resistor, which one's a capacitor, which one's a source. And I'll give you a hint, they're all present here that I've mentioned. Now, the other part that we have of the circuit is the node. So the node you can think of as a connection between two or more branches. So it's, to me, I think of it as, how do I connect, what wires do I use to connect those resistors or those parts together so that they all connect into the circuit. So you see in the black dots here, ordinary nodes. Essentially, I think of that as 2 wires that are connecting the source to a resistor, or 2 resistors together, or essentially to me that's a jumper cable that I plug into the circuit board. which we'll go through designing these later. Sometimes we don't always show all the nodes, so in the very bottom, you're going to see under, in between the power supply VS and N4, there's no node there, there's no dot. Sometimes we don't show that as well, especially on the grounding side. But just think of that, again, as a wire that connects through. We also then have extraordinary nodes. So these are nodes that connect more than two elements, or branches. So they connect more than two parts. So extraordinary nodes here are shown by the red dots. And you can see each one of these is connecting, N2 connects 4, which is pretty big. N4 and N7 each connect 3. So you can think of the red ones, or the extraordinary nodes, as like blobs of solder that connect a whole bunch of electrical wires together to make sure they're really connected, to make sure that you have current flowing in and out of that point very freely. The final part that we have here is the loop. And loops are, to me, a little bit more complicated because you can have many loops. So the one outlined in red is a single loop of the system. There's a bunch more loops. I'm counting 1, 2, 3, well, there's a lot more than that, but 3 separate loops that connect. We can go as many as 1, 2, 3, 4, 5, 6, 7. I'm counting 7 total loops in this system, depending on how you look at it. So we're going to go through loops later. Loops allow us to use some circuit analysis techniques that we're going to learn in order to help solve these circuits and complex circuits in the future.